Thank you very much for the invitation. I'm very excited to be here. It's actually my first time on your beautiful campus here in Berkeley. And what I'm going to be talking about today is some of the physics work that I do, which is understanding the structure of matter, normal matter, utilizing polarized targets. And if that's something you're not familiar with yet, that's okay, because we're going to start a lot earlier than that. So this is going to be a little bit of an overview of nuclear physics as well. And also I'm going to use, maybe not quite nuclear, but nucleon physics, nucleon being either a proton or a neutron, the things that make up the nucleus. So our understanding of doing this kind of physics for over a century at this point has changed tremendously from early experiments where our understanding of something like the proton was at the point where we thought it was maybe a point particle, to our understanding of it more closer to today, which is much more rich and deep and complex than that initial understanding was. Not only that, but the size of these experiments have gone from small tabletop experiments to experiments where you need an airplane to take a photo of if you want to grab the whole experiment. And the collaboration size has gone from just a small handful of people to many dozens to hundreds of people or more, depending on what collaboration is involved. I'll also be talking about some of the work that we're doing for kind of driving this into what I see as the future of some of this work and some of the ongoing research efforts that we're doing. So I'm actually going to start a little bit earlier with the discovery of the nucleus, which was found in Rutherford's lab. And the way that this was set up is actually really similar to how nuclear physics is still done today. You have some kind of target of interest that you want to look at. You have some kind of beam of particles that you're going to send in to scatter off of it. And you have something to detect what happens after the scattering process occurs. In doing this, there are a couple of things that are particularly useful to keep track of, such as the energy coming in, the energy coming out, the scattering angle, and this term nu is how much energy gets transferred from your beam to your target. Turns out to be really interesting. If you're not super used to this yet, you can think of nu as being how hard did we hit whatever it is that we hit. After this discovery, Rutherford spent some years during World War I kind of getting diverted from his research, going to work on radar before coming back in 1917 with an experiment where he had a vacuum chamber that he could empty out, fill with nitrogen. His beam source was an alpha source, and his detector was the eyeball of his students. At the time, they would look down this little microscope at this little luminescent screen. And one of the other pieces that they put in is they put a magnet in here as well. And the reason for that is if you have a charged particle going through a magnetic field, its path will bend, and its path will bend differently depending on the momentum or the mass of the particle. So if just the alphas were going through, if it's under vacuum, you'd expect some amount of bending to happen through the magnetic field. It's hitting nitrogen, which is much heavier than alpha, so you wouldn't expect that to bend as much. And this is kind of the reactions they were looking at. They would hit different parts in that screen. What was really interesting though, and they could not understand immediately, was that in this reaction, they were getting a whole bunch of additional hydrogen coming off of this as well. So this is the discovery of what we now know as the proton. Came out as kind of this anomalous hydrogen, is how we learned that the proton exists, that we were actually breaking up the nitrogen nucleus into these smaller components. While this work was being done, there was another man by the name of James Chadwick who actually spent World War I in an internment camp. He was actually doing work with radioactive toothpaste, height of the radium craze. Interesting things were done during that time. But after he was released in 1918, he went to work with Rutherford and became his student. And he did a very similar experiment to this one where they had the same kind of particles coming out. But what was unique that Chadwick did is he put a second chamber a little bit further away after the first one, but that did not have any source in it. So I was looking at this beam here, but all these particles got scattered down in the way. So kind of naively, you might think that you would see nothing coming through here, but the interesting result was that even in this case, having these two things be separated where you thought everything was getting bent by the magnet, they were still seeing this excess of hydrogen. What was going on? Well, this magnet should be bending any charged particles going through, so there must be some kind of uncharged neutral particle going through, and this was the discovery of the neutron. When we're talking about nucleon physics, this is kind of the beginning of this kind of field of study of understanding what are these two things, what are their properties. Very rich, interesting thing that we're going to dive through and are still working on understanding today. Both of these groups won the Nobel Prize for their work. So the question now that we found the proton and the neutron, the next natural question might come up, well, what are their individual properties? So work was done by Otto Stern, who actually studied under Albert Einstein, was one of the folks who co-discovered quantum spin, which is intricately related to magnetic field. One way that you can think about this is you can think of nucleons almost like tiny compasses that can only point in two directions, either toward, along with the magnetic field, which we can consider spin up, or against it, that we can consider spin down. Because it's quantum mechanics, it's quantized, so you only have these two different spin states for a spin half particle. And looking at the magnetic moment for the proton, one of the strange things that he discovered was that the proton's magnetic moment was almost 3 times larger than it should be if the proton were a point particle. So this is our first hint that there might be something more in the proton that makes it more complex than we thought it was. Of course, as happened to many research groups in this era, the rise of Nazis to power interrupted a lot of research. Otto Stern actually fled from Germany to Pennsylvania during this time frame, and a lot of effort for scientists of the time went into the Manhattan Project here in the States. It's actually a guy by the name of Robert Oppenheimer, you might be familiar with from the Manhattan Project. If that history had been a little bit different, you'd probably know him more for black holes research afterwards, and kind of following up with trying to make bigger bombs, issue with McCarthyism kind of coming through from the 1950s. A lot of this has diverted nuclear physics away from the study of protons and neutrons and into this kind of development. So we have a little bit of a hiatus. 1950, there's actually a postdoc at Stanford by the name of Rosenbluth who started kind of going back through and developed a method where we could better understand this hint of substructure that was hinted at before, how we can understand what's actually going on inside the proton. I actually went to work for Teller after this, but what he found was what he developed was a method to use elastic electron scattering from nuclei to better understand what's inside them. So what do I mean by that? Well, in order to do this, we need to measure something called the cross section. We think of this as normalized number of counts. So like I said before, we have some beam, we have some target, we have some detector. And in that detector, you can measure how many counts of particles are going into that detector. Of course, there are a number of things that could change that number of counts. The only things we want are what's related to the interaction and get rid of the things that aren't related to the interaction. So one thing that you could change the number of counts is if you have twice as many beam particles coming in, that would double your number of counts out. So we want to cancel that out. You could have it hitting twice the number of nuclei. That would change the counts, but has nothing to do with the interaction. These two things we bring together and call the luminosity by this fancy L term here. So we're kind of canceling those out in this cross section in order to get rid of that effect. But of course, you could also let the experiment run twice as long and you get twice as many of events, and that has nothing to do with the physics. So we cancel that out in our cross section as well. And then what we're left with, ideally, is just what is related to the physics of the interaction of what we want to study. So if we have a point-like particle, we measure its cross section. If it is a point particle, there is a cross section that describes this called the Mott cross section. So if the proton was a point, we would expect it to just be the Mott. Where Rosenbluth comes in is he adds these additional terms that can explain deviation from this point-like structure. And in particular, he has these two structure terms called form factors that give us information on the electric charge structure and the magnetic charge structure inside the proton and neutron. These points in pink in here are related to kinematics, the experimental setup for what's going on. And in doing so, we were talking a little bit about how hard do we hit it with energy transfer. I'm going to introduce a new variable, Q squared. This is the form momentum that gets transferred to the target. What's important about Q squared is it's related to the resolution of your probe. So the higher the momentum transfer, you go through a Fourier transform, the smaller the thing is that you're looking at. So higher Q squared goes to better resolution of your probes. And we'll come back to that. So the theoretical work for this was done by Rosenbluth, and then some of the early experimental work for this comes from Robert Hofstadter, who built experiments at Stanford using Rosenbluth's method. He had a large expertise in detectors in particular, creating these automatic sodium iodide scintillation counters, so that way his students didn't have to look through the microscope quite the same anymore. We now start letting electronics do the counting for us. Here's a photo from the beamline that he utilized in a little schematic to give you kind of a sense of what's coming in here. And we see, once again, a similar kind of scattering target, like I've done before, a detector hut down here. So we have a beam, a target, and a detector coming in. And he won the Nobel Prize for this work here. That was the first true experimental evidence, kind of building on what Otto Stern's work hinted at, that the proton is not a point particle. If it was a point particle, particularly in these higher angles, it should have followed this dashed curve down here, and all of the data was following a different curve. So that gave us kind of our first experimental proof that this is not a point particle, and now we have a way of studying it. He also noted that not only are nuclei built up out of protons and neutrons, but it's fascinating to think what the proton itself is built, and further mentioned that the proton, the deuteron, and alpha particles are the most interesting to study because they are among the simplest nuclear structure. And for the deuteron in particular, kind of hold that in the back of your head for now. So in order to understand these properties with these tools, with the proton, it's nice. We have hydrogen available to us as a proton target. Protons are charged particles, so we can send them through magnetic spectrometers, just kind of more advanced versions of what was shown before, of different focusing magnets to get more complete information about what's coming out. We have these two unknowns that I mentioned. So if we have two unknowns, if we take two measurements at the same Q squared, but otherwise we're changing some of these other numbers in here, we can get, we can solve for what these form factors are using this method. So in doing this, has given us our understanding of these form factors versus Q squared. Remember, Q squared is related to resolution, higher Q squared, smaller thing that we're probing. For ease for a lot of this, so we're looking at the proton on here, and we're also looking at the proton's electric form factor and the proton and neutron magnetic form factors. And we can compare them to dipoles because they look quite like a dipole. And if we put a dipole curve on here, it's going to look something like this. And part of the reason why we do this is we now have a simple model that we can scale it to. So if we divide the real data by this simple model, anything that deviates away from 1 would show us that this is a region where the model doesn't work as well. So this is directly related to, we see this 2.79 here, that anomalous part goes back to what was talked about earlier, but now we're actually probing it more directly and understanding this structure more deeply. I mentioned that. So these plots are the proton electric and magnetic form factors divided by that dipole. So deviations from 1 would show deviations away from our understanding of it theoretically. And for the electric form factor, it seems like things are pretty close to 1. It seems like this model works really well for it. For the magnetic part, there's definitely a bit more going on here, particularly at the higher squared region. But by and large, it seems like this model is also working well for that. So this is with this Rosenbluth separation technique where we have 2 unknowns, 2 measurements, all unpolarized to get these measurements. We can also do a Fourier transform of this in order to go from momentum space into position space to learn more about what is the electric structure inside the proton. And that tells us that inside the proton, we have this big positive core that kind of dies off as you get further and further away from the center. So we can actually start building up the internal structure of what this proton might look like that has some particles inside of it that make it up. We can do the same thing for the neutron, but it's more complex because we don't have a free neutron target available because neutrons decay pretty quickly, not inside of nuclei. They're also neutral particles, so we can't use the magnetic spectrometers the same way. It makes them much harder to detect. They also have a very small electric form factor, not unexpected because they are neutral particles. Very hard measurement to do, but nevertheless, number of measurements were done. So you're looking at these measurements here, and you see that the error bars on these earlier measurements are much larger than we had for the proton because of all of these challenges. However, you still take this data, do the Fourier transform, you get what looks like a positive core inside the neutron with a negative outer shell around the outside of it. So what we learned from this kind of on a more deep level is that whatever this substructure is making up protons and neutrons, that substructure is charged. It's made out of positive and negative charged particles. Continuing along, we have a new variable called Bjorken X. It's the scaling factor. What's important to this way I like to think about this is this relates that Q squared term to the mass of the proton times the energy transferred. And you can roughly think about this as how big is the thing you hit scaled to the size of a proton. It's not exact, but it kind of gets you in the ballpark. So if we hit something that is made up of protons and neutrons, let's say we hit a nucleus with 12 total protons and neutrons, 6 and 6, then we would expect a big elastic peak at x of 12. As you go down a little bit, there would be nuclear resonances that come in from not purely elastic scattering. So you see these additional excitations. What's important is as you're near that elastic peak, you're probing the nucleus as a whole. You're probing full nuclear effects. As you get down closer to x equals 1, you're scattering off of 1 proton or 1 neutron. So we see nucleon effects. We have this nice big peak, but it spreads out. The reason it spreads out is because these protons and neutrons are interacting with one another. So it's not just this one thing sitting on its own. It's all these small parts that are interacting with one another, smearing out that peak. So we get a wider peak within here. And as we go down to the low X region, we can actually probe deeper and deeper, or smaller and smaller pieces, actually going into the subnucleon effect. So we knew that these things are made of positive, negative charges from the form factors. This type of scattering now gives us a new way to study these things more directly. So similar to what Rosenbluth did, we have a new way of looking at these through what are called not form factors, but structure functions. So similar to before, we have these kinematic terms, and we have these 2 additional terms for structure functions that we can look at. So these describe information about the electric magnetic parts of these things we're probing. And really, they're describing what's inside the nucleon. So F2 in particular, I'm going to kind of walk you through a little bit. I'm going to show you the data first and then walk through how we understand this data. So this is early data of this F2 structure function for the proton versus that Bjorken X term. So if we were to look at building a theory to explain this, if we had that initial point particle hypothesis, then what we would expect from F2 is that there would be not a whole lot going on except that all of the momentum would be carried at x of 1 if it was a point. This plot doesn't even go to x of 1 because it gets boring out there. So this isn't what's happening. Instead, it looks like the main peak of this is coming down quite a bit further. We can get closer to this if we think of the proton as being made of 3 point particles we now call quarks. That starts getting our peak kind of closer to the peak of what our data is showing, but it's still way too sharp for what we're seeing. Just like we saw the interaction smearing out that quasi-elastic peak, if these point particles are interacting with one another, the peak would smear out from a very sharp peak to a much wider peak. And at this point, for kind of smearing this out, we're starting to see what the data is showing us, particularly on the right-hand side of this. For the left-hand side, we're still not dying down quite the same way that we would expect from this. How do we explain that? Well, if we don't let these 3 interacting quarks be the only things that are there, if there's also what we now call a quark C, a quark anti-quark C, point particle quark anti-quark pairs that come into existence for small points in time, but are able to interact with these 3 interacting quarks that are kind of the more stable ones. That brings up this low X region for this, what we call the quark C. And now we kind of have an understanding of, from this understanding of what we're seeing inside the proton, we're now matching what the data is showing us. So this is giving us information of how these things appear inside of the nucleus, how we know the quarks are there. Again, Nobel Prize winning work for this. The F1 term describes magnetic interaction inside of the quarks. So I mentioned before that magnetism and quantum spin are deeply connected to one another. If quarks were spin-half particles, then if we divide these 2 structure functions by each other, multiply it by x, that should equal 1/2. But I'm going to rearrange that to make it equal to 1, because like we saw before, setting things equal to 1 and seeing where they deviate is often useful. So that's what you're seeing on this plot here, is this term here. And the fact that we're equaling 1 here means that this equals 1/2. This is giving us information about what the spin is of the quarks. So our this particular relationship is known as the Callan-Gross relationship. And this gives us information on what is the spin of the quarks. And now we know that they're in there. There are 3 kind of stable ones. There's this quark, anti-quark C. It's suddenly become a lot more complex of what is happening inside the proton. So we learn that we have these 3 what are called valence quarks, and the more stable ones. We also didn't mention this directly, but we learned that there are 2 types of quarks, at least in the nucleon, spin up or up and down quarks. So the quarks are spin half and they interact with this quark C. So relating to spin, particularly since there's spin going on with these quarks, maybe we can use that as another way to study what's happening. So with these new degrees of freedom with spin polarization, we have new ways of being able to study these effects. So with polarization, we get not just cross sections, but ratios of cross sections that become useful, where we can put our target in or our beam in one spin orientation, take a bunch of data, take it another way, take a bunch of data, and then look at a ratio between that we call an asymmetry. So we take the spin in one configuration minus from another and divide it by these 2 things added together. The reason this becomes useful, and we can put it back in terms of these form factors I mentioned before, is that because we're doing a ratio, anything that's the same in these cross sections will cancel out. Not only will they cancel out, we're also subtracting them as well to really get rid of anything that's the same between these, and anything that is different we are emphasizing. So we're trying to pull out more subtle effects with these asymmetries. This leads to, in part, the creation of Jefferson Lab, where a lot of this work is being done. And I really want to emphasize that the vast majority of what we know about the nucleons comes from either cross sections or asymmetries, these kinds of measurements. If we want the bulk properties, we use the cross section. And if we want specific interactions, we use these asymmetries. So we can remeasure what we did before with these spin effects at Jefferson Lab. This was the photo of what I showed earlier. This is a fixed target electron accelerator. It's about a mile-long racetrack for the beam. It can go around currently up to 5 times. There's plans for improving that. These 3 big hills that you're seeing are the experimental halls, and actually there's a 4th one now way back there. What it looks like inside of this is actually shown on the right here. There's a rough scale of a person, big cylinders dug out underground with detectors the size of train cars on big tracks that we move around to study these. So anyway, getting back to what we were talking about before, we can we mentioned the Rosenbluth separation technique. I mentioned this new asymmetry technique. We can measure the same observables. So since we have 2 unknowns for Rosenbluth, we need 2 different measurements. I mentioned with Rosenbluth, for asymmetries, we can do different kinds of asymmetries in order to get the different ways of canceling them out, so we can get information from both polarized beam plus polarized target, or polarized beam and proton polarimeter. And what's interesting when the data was taken on this is all that beautiful Rosenbluth separation data that looked like it agreed really well with the dipole. When we look at it with spin, oh dear, it dropped off dramatically. In fact, kind of going to entirely different from what the dipole was. So our understanding that we thought of what we knew is going on with this electric structure in the proton completely changed once we had access to this new spin degree of freedom. And this big discrepancy led to all these little subfields of physics popping up, perturbative QCD, generalized parton distributions, quark angular momentum, all interesting things going on that we really came about because we looked at the same system that was measured before, we thought we knew well, in a new method that has completely changed our understanding of it. If we look at the neutron, these are new neutron measurements that were done. Our understanding of the neutron similarly has changed with spin polarization that gives us better measurements. Remember before we had that positive core and that negative outer shell. With this newer data, particularly going out to this higher Q-squared region, as we dig in further, it turns out that the neutron has this huge negative core as well that was newly discovered thanks to developments with spin polarization. So our understanding of the electric structure of the neutron also completely changed with these new effects. If we then go into what's happening here, let's look in the deep inelastic region where we have those structure functions. These F1 and F2 are done with an unpolarized target. If we now polarize the target, we actually get 2 new structure functions, not just F1 and F2, but what are called G1 and G2 that are giving us more information about what the quarks inside the proton and neutron are doing. So looking at a cross-section difference instead of a ratio in this point. So we have the beam and the target polarized together minus the beam different from the target. And what this difference in cross-section is related to are the momentum distributions of the quarks with various spin inside of the proton and neutron. That's what the G1 structure function gives us information to, is not just do they have a particular spin, but where is that spin inside of the proton and neutron. Huge amount of data has been taken on this. A lot of effort has been done. This gives us information about the quark spin distribution inside protons and neutrons. And what we've learned from this, hugely important, is that those 3 valence quarks, the things that are stable, do not make up the spin of the proton. In fact, there's this what's called the spin crisis, where we only know where a fraction of the proton spin is coming from, and trying to understand where is the rest of the spin is an ongoing effort within nuclear physics that we're still trying to find a full answer for today. The G2 structure function, not quite as simple an interpretation for this. I will mention it's split off into two parts, one entirely dependent on G1, another one that gives information on quark-gluon interactions. So it might be able to uncover some more information about what's happening with not just the quarks there, but that interaction term, the gluons causing that interaction. We can learn more from this observable as well. And there's actually a group at UNH that has done this, actually just recently published a paper on this. That kind of gives you a rough state of our understanding of where we are in our understanding today of these things. What I want to talk about is where we go to next. And from my perspective, since that first new degree of freedom of spin has completely changed our understanding of the proton and neutron, there's another degree of freedom also related to spin that we can use that I think can open up another new avenue. And this is called tensor polarization. So what the heck is tensor polarization? Well, polarization generally, as I mentioned before, for a spin half particle is if we have, we take the number of nuclei that are in one spin state minus the population in the other, that gives us our normal, or what I call vector polarization. Tensor spin polarization only exists for spin 1 or higher nuclei. And the reason for that is we don't just have a spin up and spin down, but we have the spin 0 case. And a lot of our work is on the deuteron that I mentioned earlier. One way that I like to think about this is for the deuteron, the spatial distribution actually changes depending on what spin state you're in. So if you're in the +1 or -1 spin state, it has this more peanut-like configuration. And if it's in the spin 0 state, it has more of a donut-like configuration. So the way I like to think about tensor polarization is that tensor polarization is we take the two peanut states, add them together, and compare them to how many donuts we have. So do we have more peanuts or do we have more donuts? Is how I like to think of tensor polarization. So if we have more peanuts than donuts, that is a positive tensor polarization. We have an equal number in all three spin states that is unpolarized, so 0 polarization. And if we have more donuts than peanuts, that would be a negative tensor polarization. One of the other odd things about tensor polarization is that it can go not just from +100% to -100%, like normal vector polarization, actually go to -200%. And that comes from this extra factor of 2 normalization term, because there are two of these kind of competing for that one that let this unpolarized state exist. But anyway, if we have more peanuts than donuts, that's what we're looking at. For the experiments that I'm mostly going to be talking about, we're going to be comparing a positive tensor polarization to an unpolarized case, because getting this bottom case working in a beamline is extremely difficult. But if we can have a high luminosity target, remember beam particles in or density of what we're hitting, we can probe, we have a new way of probing nuclear physics, and we can learn some new things from this. So if we go into that DIS region, again, those two structure functions that we got from doing spin polarization, go to tensor polarization, there's not 2 more, but 1, 2, 3, 4 new structure functions that we can probe. So B1 is the first one of these to be measured. And one of the interesting things about this, as we go to this high X region, we expect this B1 observable to become very, very small, very close to 0. And any conventional nuclear physics model, all of them were making this prediction. This prediction greatly disagreed with the first data that came in from Hermes on this. However, I will note that the error bars on this away from 0 are only about the 2 sigma level. So there's kind of an open question of, is this a statistical fluctuation, or is this something new that can give us a new avenue into some new effects that we're trying to understand? We can also, from this, what are some of these exotic effects that maybe this is indicating? We might have effects related to that anti-quark distribution. The polarization of those C quarks might be in part responsible for what's happening here. There are also predictions using 6 quark hidden color effects. So the deuteron is a 1 proton, 1 neutron, and this would be a configuration where it's not a proton plus a neutron, but a more complex configuration of a 6 quark state versus 2, 3 quark states near each other that can lead to understanding this anomalous point. But we need better data on it. So we're going to be taking better data on this at Jefferson Lab. This is part of the research program that I have with them that we actually just recently got fully approved in building this target moving forward. Another thing we can look at, another interesting development in nuclear physics over the last couple decades, is something called short-range correlations. And the way that I like to think about this is in short range correlations, everything seems to look like a deuteron. So if you take any nuclei, so helium, beryllium, carbon, copper, gold, and divide that by the cross section of the deuteron, there is a region where these become flat, meaning that there is a region in the cross section where every nucleus is looking like the deuteron. So that makes, going back to Hofstadter, the deuteron a really interesting thing to study. It's the most simple system. So we're going to take a look at this with tensor polarization. If we want to understand what's happening with these short range correlations, the two things that we could do to probe effects going on here is we can look in these x greater than 1 kinematics like these experiments here are showing, or we can change the tensor polarization that turns on, enhances or suppresses different spin states to get information. So we're going to combine both of these techniques into a new experiment that we're going to be running at Jefferson as well. So what we can do with this, the power of this is this, the observable we're looking at is AZZ. It is a cross-section ratio. So these are the tensor polarized versus unpolarized. And what we're looking at here, one of the two interesting things we can get out of this is the curves in red are with the light cone model, the curves in blue are with the virtual nucleon model. Basically, these are two models that are used to explain the relativistic effect of what is making these short range correlations happening. And if we do unpolarized measurements, we can't well separate them. But with tensor polarization, we get this nice separation where we can distinguish them. Not only that, but if we put in different wave functions of the deuteron, where the different wave functions, one of the things they have different in them is when you get the proton neutron together, the strong nuclear force binds them, but if you get it too close together, there's actually a repulsive core that's pushing them back apart. And is that repulsive core, does that have a slope that is kind of going up? It's going up fast, but is it kind of a slower fast, or is it a super steep curve? We're kind of looking at the difference between there is looking at the difference between the AV18 model and the CD bond model as wave function inputs to these. So not only do we see the separation of the blue and red curves at the lower x points, but as we go to higher x, we get this big difference in here as well. So it's a very unconstrained region theoretically. So this is the argon wave function model for nucleon-nucleon interactions. So yeah, so this the AV18 is uses a harder wave function potential, so a sharper peak of that nuclear core than CD bond, which has a bit of a less sharp one. So you're looking at the difference between a harder wave function and the softer wave function. Those are just some of many different theoretical calculations we have, because with this tensor spin observable in this kinematic range, lots of different theories. It's unconstrained. There's a lot of interesting things going on here that I don't have quite enough time to go into detail, other than say we're measuring this at Jefferson Lab as well. I also mentioned that in order to understand this, since everything looks like a deuteron all the way up to heavy nuclei, continue that on to the super heaviest of nuclei, neutron stars, understanding the short range part of the nuclear force can be important for understanding the equations of state of neutron stars as well. So there's this really deep connection where we can take something super simple, one proton, one neutron, and use that to understand some fairly massive objects a little bit better as well. So we want to build a polarized target to do this. I'm going to go through this a little bit quickly, so apologies for that. I mentioned that we have the polarized target we're trying to build. I'm going to talk about proton first, because it's a little bit easier to talk about. So we have two spin states, spins related to magnetic moment. So if we put a proton inside of a magnetic field, we get an energy level splitting that occurs. So with no field, they'd be at the same. If we put it in a B field, we get this energy level split and occurs. And generally, things are more likely to be in the lower energy state than the higher energy state. So this, we get what's called a thermal equilibrium measurement that's just dependent on the magnetic field that we're putting in and the temperature. So if we want to increase polarization, we can change these two things. If we're at room temperature, and let's say we had a fridge magnet, we get an extremely tiny proton polarization. But if we make the temperature go up, or temperature go down, field go up, we get a strong magnetic field, like a 5 Tesla superconducting magnet we have in the lab. Temperature we bring down to about 1 Kelvin using a liquid helium refrigerator. That increases our proton polarization quite a bit, but it's still only about 0.5%. So it's a lot better than we started with, but it's still quite small. So we can really get that to a higher percentage number, we can start doing something useful. What's interesting is that the electrons in these conditions have almost 100% polarization. So the trick for building these targets is to transfer the electron polarization to the nuclear polarization. So the way we do that is if we look at the energy splitting of electrons, we can introduce paramagnetic centers in order to create a coupling effect between the electrons and the nuclei. And what we can do with that is we can actually bombard this with microwaves at particular energy levels to drive electron spin transitions. And since they are coupled with these nuclear states, we can actually bring the nuclear states along for the ride. So if we couple from this middle state where we have protons being in the down state, and we drive a frequency of the electron transition minus the proton transition, we can actually drive a large positive polarization. Or if we do this larger energy gap, we can drive a large negative polarization. So we can use the electrons to get a high proton polarization. In fact, we can, with this method, get nuclear polarizations upward of 90% or better. With the deuteron, which is what we're interested in, we have 3 spin states, so it looks a little bit more complicated. And not only does it look a little bit more complicated from this, but we need to be able to separate one transition from the other. And if they're equal distant to one another, they're overlapping, and it's not helpful for understanding tensor polarization. So we have nuclei that have an additional quadrupolar electric interaction that causes additional splitting, that actually splits these 2 states into different ones. It becomes a lot more complex. I don't want to go into a lot more detail. It's basically the same process, but harder to drive. And not only is it harder from this splitting, but because we have a random distribution, you actually get this huge distribution of a number of different theta bins. I'm showing kind of 2 as an example here as these things change. So we actually get this much more complex measurement when doing this with NMR, where we get these 2 different peak transitions. Going back to tensor polarization, how do we get that? Well, vector polarization, if we measure the total area, that tells us the amount of vector polarization. To get the tensor polarization, we want to look at the difference of the green area compared to the yellow area here. And if we want to enhance tensor polarization, we want to minimize the yellow while increasing the green. So that can increase our tensor polarization to get that positive tensor polarization that we need to run those experiments that I mentioned. So there are techniques to do this with RF manipulation. Interesting thing is when you apply RF at one point in the NMR spectrum, because these 2 peaks, you can see they're kind of mirror images of each other. That mirror is related to the quadrupole angle theta that I mentioned before. So affecting it here, driving it down here actually causes a bump up on the other side, which is great because we want to decrease the yellow while increasing the green. So that actually happens in doing this kind of manipulation. And their colleagues at the University of Virginia have demonstrated this recently with fairly high tensor polarizations on the order of about 30% using this method. In addition, we can then rotate it to drive this polarization throughout the rest of the nuclei to get even higher tensor polarizations. So this technique was developed, like I said, at the University of Virginia. I'm from the University of New Hampshire. Our group is actually kind of started from work that was done at University of Virginia. One of our early target group PIs worked with Virginia group before coming to New Hampshire, starting our new polarized target effort. And we now have a similar polarized target at UNH, where we've been doing this as well. We have that magnet and fridge I talked about. We have a new unique solid state microwave system for driving these spin transitions. We're doing fun things with 3D printing that survive all of these intense conditions for our target material. We are doing both tensor and vector and tensor enhancements at New Hampshire. We started our first deuteron measurement. It was actually only a couple of years ago. So we're behind the UVA group, but we are kind of quickly playing catch up. and helping out with this polarized target effort. We've gotten electron EPR measurements within here as well, which is really useful for understanding this electron transition better as well. I think I'm going to just skip through a bunch of these for the moment in the interest of time. Just get to the overall summary of what we're doing. Kind of the whole point of all of this is going back to understanding what is a proton, what is a neutron, how our understanding has grown tremendously from a guess of an initial point to the massive, rich, detailed structure that we know is inside of them today. And using that going forward of how can we further probe and further ask new ways of looking at questions related to these unanswered questions. And this work would not be possible without the massive effort of students, researchers, colleagues, both at the University of New Hampshire and at the University of Virginia. So with that, I will say thank you. So it depends on a variety of different conditions. Our polarized targets were primarily running at 5 Tesla, 1 Kelvin. The lifetime there, if we were to turn it off, the proton measurements would decay over the course of a couple hours. The deuteron decays a bit longer. But if you put it in a beam line, there are effects from beam heating that cause that depolarization to happen quite a bit quicker. So when we're running our experiment, we're actually doing this DMP pumping basically constantly all the time while the beam's running. So we're not putting it in like a frozen spin state and then running the experiment. We are continually driving this process while running our experiments. Yeah. It's significantly more, yeah. Yes. So why not? Why not go colder? Yeah, yeah. That going colder would get us to the higher polarization very, very easily. The problem with going to lower temperature is that the refrigeration mechanisms to hit that low temperature don't have as much cooling power when you're starting to heat the material. So the problem for us is that we have the beam on it that heats it up, and that we need to cool it down to maintain the polarizations that we have. And the evaporation refrigerators that go to 1K that we're using have a higher cooling power than the dilution refrigerators that can get much colder temperature. We actually we don't do strobing directly. We do rastering to help with that so that we're not heating the same part over and over again. You can also reduce the heating effect not by using an electron beam, but using a photon beam facility. So if you use a photon beam instead of an electron beam, you don't quite have the same heating effects going on. There are other experiments that are doing that for, I know a lot of spin half experiments do that. There are occasional spin 1 experiments that do that as well. Everything I described is with an electron beam. So you would have to rerun the interactions to understand how it would work with a photon beam versus an electron beam. One of the really nice things about the electron beam is that the electron seems, as far as we know, like a point particle, which makes it the interactions coming from it easy to understand. So that way, when we're looking at the cross section from electron scattering, the electron part of it we can consider known. So we're really only probing the nuclear part. Depending on what you're hitting it with, that might not always be the case. Right, right. And one of the other hard parts with a photon beam is actually knowing precisely what is the energy of the photon beam, because usually you have something like an electron beam that you will scatter through some material and then bend the electrons away, and then have the photons propagate from the bent electrons. But it's much harder to precisely know what the energy is of that photon because you only have some distribution of the bent electrons that come out of it. So it reduces some of the known properties when you move to a photon beam. So at the moment, yeah. So the one with that in particular that I'll mention, our leading thought for what is happening with the B1 in particular. So assuming that point is real and not a statistical fluctuation, is that what's going on here are effects that might be related to the 6-quark hidden color distribution. So this would not be necessarily standard model breaking, so not beyond standard model, but properties that might be expected of a standard model that are subtle and haven't been experimentally observed previously. There have been previous searches to look for these 6-quark hidden color effects that have not seen direct indication that this is happening. So there are already constraints on this model. What's unique about this observable is even if you have a very small, like you go an order of magnitude below the existing constraint on these interactions that we know from previous data, you can still get something that looks like it's going to match, if assuming this data point is real. So this is our first kind of full theory that we have, trying to see what's going on here. So it's a little bit away from conventional nuclear physics because these effects have never been directly observed before. But even constraining them well beyond the known constraints, because of the tensor interaction, we can actually still potentially probe these coming out here, which is kind of unlocking this as this kind of new window, this new degree of freedom for hopefully opening up not just this avenue of understanding, but potentially down the road for more complex, more interesting physics down the road as well. It can. So the Q squared is related to the energy of your beam. Ah, excellent. Yeah. Yeah. So the question was related to one, can you change the Q squared? Does that change the angle, the scattering angle? So that's one of the things that will change the Q squared term. Q squared is equal to -4 times the beam energy. You can also change the beam energy. E prime, which is the scattered electrons energy, that can change, and sine squared, that's scattering angle too. So there are 3 different variables that you can manipulate in order to change the Q squared value. It also means that if you change the scattering angle and the beam energy, you can get the same Q squared, but at different kinematic settings. That Rosenbluth method I mentioned earlier, that's what they're doing. They're keeping Q squared the same, but changing both the scattered beam energy and the angles. Keep the Q squared the same, but still have 2 different measurements at the same Q squared in order to extract that information. Yeah. Yeah. So this paper here is where our understanding of this comes from. So I mentioned kind of earlier, our understanding of the form factors gave us our electronic structure of the proton and the neutron. With the deuteron, we have form factors, not quite the same ones. There's an A form factor, a B form factor, and a T201, which I also haven't talked about. Basically, we have different form factors that look at giving us information into what is the structure of this nucleus. And what this paper went into detail about is that utilizing those 3 form factor measurements looked at what that would mean for the spatial distribution of what this nuclei looks like. And if you run basically these Fourier transforms or something similar to them from these form factors, particularly ones that are dependent on the spin state, that you get different distribution depending on which spin state you're looking at. So a very, very naive way, super naive way to think about this is, you can almost think that in the peanut-like state that we have almost a separation where maybe one of these is the proton, the other one is a neutron. Of course, it's a superposition, so it's not quite that, but kind of think of it that way. And in the spin 1 state, these things aren't quite spinning, but you can almost kind of imagine them around a center of axis this way. In the spin 0 state, one of these gets rotated down, and now they are in a superposition that is not kind of rotated with kind of one on top of each other, but one next to each other, kind of mapping out this more toroidal structure. There's kind of a little bit of a hand wavy way of doing it. The more correct way is what they do in this J. Forrest paper, but it might give you a sense of how we can get this information from those form factors going through those Fourier transforms and why those might be connected to the various magnetic structure, which relates to the spin structure.